So, g'day, I'm Andra Keay. I'm Managing Director of Silicon Valley Robotics and a visiting scholar at the Citrus People and Robots Lab. Firstly, I want to open tonight with the acknowledgement that I'm here on the lands of the Ohlone tribe of the San Francisco Bay Area, who are a federally unrecognized tribe, but certainly predated other visitors. Myself, I'm a very late visitor to the Bay Area, so you'll probably detect an Australian accent, and hope that's okay. We have enabled the transcript for people who are potentially hard of hearing in our aim to be more inclusive. And in fact, our discussions are very much about the issue of what is inclusive robotics? Who has it? How do we get it? What does it entail? And what do we need to do to make robotics inclusive? And we've looked at this from a range of perspectives, from robotics and racism to robotics and some of the latest advances that are going to be assistive and potentially augmentative. And so after a really great discussion last month with people about the topic of assistive robotics, we wanted to address more closely the topic of prosthetics, of powered clothing, and of exoskeletons. And I'm delighted to have some amazing pioneers, entrepreneurs, artists, technologists here who are able to speak to a range of the newest advances in the areas of, as said, prosthetics, powered clothing, and exoskeletons. And so rather than try to explain what those three terms mean and why they're different, I know that our speakers will be able to help. The speakers that we have today, Scott Summit, who's the founder of Ethereal Matter, and an industrial designer, TED speaker, and artist. And Scott founded Bespoke Innovation in 2010, creating the first 3D printed prosthetic fairings, and he's coined the term fairings. So I'm really pleased that Scott was able to join us today. We'll be hearing from him first, and he'll be able to explain a little bit more about what a fairing is, in fact, and perhaps what he's working on right now. And then we're joined by Michelle Malouf, who's a corporate development for aging and senior care, a consultant in these fields, and previously with exSeismic, which is one of the very, very interesting powered clothing companies that is in the Bay Area at the moment. And what I love is that Michelle brings not just the experience of the technology, and this is very innovative technology, but she brings the perspective of what this means to certain communities. And so I'm very much looking forward to that. And then we'll be joined by Yves Nazon, who is a graduate researcher in Neurobionics at the University of Michigan. And he's so many things there. Okay, cutting it short. Yves is an NSF graduate research fellow and is currently pursuing a PhD in mechanical engineering in the control of exoskeletons. And then we have Hamayal Choudhry, who is the co-founder of smartARM, a very new prosthetics company that has been making a great impression in, I believe, winning the world champion Microsoft Imagine Cup out of, I can only assume, many, many, many entries. So a world champion idea, and you've only been doing this for a very short time too. So a fantastic story and a great ambassador for Canada. And I know Canadians are very proud of their robotics, just as a fellow kind of Australian is also very proud of our robotics. So it's a pleasure to have somebody here. And without further ado, I'd like to ask Scott to tell us more about Bespoke Innovations and the work that he's currently doing now. Scott, over to you.
Hi, everyone. Thanks for having me here. I will be the token speaker who really knows nothing about robotics here. So I'll explain a little bit about the circuitous route that got me here. I'm an industrial designer from Apple and all those kind of studios and places. And everything I do is visual. So I'm just going to share my screen because that's the way I think best. So let's see. There we go. Okay. So can everybody see me? Is this working? Great. Okay, so my experience, my overlap with robotics kind of ironically started by meeting this woman about 15 years ago. And we had a long discussion about her legs, which are kind of awesome, as are that pair as well. They're kind of cool as well. What was interesting though is that while I felt that this pair artificially tried to be too human and got into this strange uncanny valley zone, this pair looked like it was never really meant to belong on a human, that I've got vacuum cleaner parts in my Dyson that are better looking than this. So I thought, this is strange. And so this becomes catnip for the industrial designer in me. So I started looking at why can't it be something like this? You know, which ironically is a source of a lot of prosthetic legs that I later ended up working on. Why can't it be something that is unapologetically man-made? Something that corrects something and offers a functionality that we don't normally have, but makes you feel more beautiful, that really treats the human body as the work of art that it is, that really plays up the individuality and the uniqueness, and that doesn't really disrespect the person with simply raw utility, which I always found that these did. You know, life is hard enough to have a prosthetic limb, let alone to have this replacing what should have been human. So this was about 12 years ago, and I started working on a process of 3D scanning the body, which was trickier at the time. Now it's very easy, and then using that morphology to then guide the design of a prosthetic limb, what I called a fairing, the non-load bearing part, which recreates the person's morphology, but also does so artfully, and does so with a lot of infusion of the person's personality in them. And so that alone had a certain value because it addressed the psychological morbidity to prosthetics and to limb loss more than anything else, in the sense that Deborah here hadn't worn a skirt in 10 years before this photo shoot because she didn't want anyone to know. She had lived in a kind of closeted amputee life. And now all of a sudden she loved it. This guy started really wanting to showcase and celebrate his leg. He wanted to make it look like a part of his motorcycle, which was what lost his leg in the first place. Chad wanted to play soccer again, and he always wore shorts, but he didn't like the unwanted attention part of it. Now he got the attention he liked. This guy, Yves, he wanted his tattoos back. So we recreated his tattoos in 3 dimensions and in 2 dimensions. This guy, he just wore a lot of herringbone tweed, so we kind of matched his clothing style. A soldier from Iraq, he wanted his musculature captured in the limb. This guy does a lot of graffiti art, so we wanted to create essentially what the graffiti art would look like if the body was missing. Interesting timing today. This is a Boston Marathon bombing victim. She lost her leg in the last seconds of the marathon, and so we just wanted to really recreate her beauty and to give her something that she could look forward to putting on. Actress in Hollywood, she wanted fishnet stockings, but out of chrome. So we did those. And another actor in Hollywood, I kind of wanted to see how far I could push this into just being a really beautiful piece of leg. And what was interesting about John Siciliano here is that when his girlfriend came to the photo shoot, she kind of smirked and she looked and she said, I like your right leg better than your left leg. And we all agreed, yeah, that his right leg really did outshine his left leg. And we walked around Los Angeles and everyone seemed to agree. So that was new and different. That was just the beginning, though. Really, the goal was to address the limb loss in developing countries, because unlike the United States, people in developing countries typically need legs more than we do, have often less access to medical care, and that gulf is actually is increasing. That the number of doctors who are capable of giving decent care is actually on the decline, and the number of people who need legs is a higher proportion of the population than the US, and they need them more because the US, most of the US, you could cut off their leg and no one would notice for 6 months anyway. So this was a process where we could 3D scan the limb, send the morphology to the cloud. It would automatically do landmark and feature identification. It would then run it through a parametric and generative model that would create morphology or geometry then, which could be sent to a printer that had discretionary bandwidth anywhere in the world, and it would print a functional leg. The idea was to take all humans out of the process. That turned out to be an interesting endeavor. We also wanted to infuse generative modeling and topology optimization, which dovetail nicely with 3D printing. So this had followed Wolff's law, which governs the strength of a living object. We want to see, could we do that with a printed object? This is now actually in permanent collection of the Cooper Hewitt Museum, and you'll see it on display there in New York. A guy lost his leg to a terrorist bombing in the Philippines. And the challenge that we found was that, let's see. Oh, yeah, so here's what we wanted to do with, was to infuse it with topology optimization. If anyone's unfamiliar with topology optimization, it goes something like this. It's a distillation of 30 million years of Darwinian evolution. Don't say that in the southern states, but we're not there and we can say this. And you can do it overnight on a computer. Basically what you do is you relinquish the design to the software and you put the forces in advance, the build envelope. The software then overnight gets your computer hot enough to cook pizza and then gives you the geometry that is optimized. It generally looks like something out of Alien 2 or the roots of a banyan tree, but that is what nature would do if it was designing a skateboard. So it lends itself very well to 3D printing because inevitably it comes out as very, very complex geometry. So we wanted to have this as a nice automated process, and I was able to do a handful of legs this way. It turns out that removing a human from the equation as far as the doctor is just incredibly hard. I was very naive going into it, and I didn't realize just how complex a prosthetic limb is. Then in the process though, somewhere I was approached by Russ Angold, who's the founder of exobionics. And he is actually my current business partner with my new venture, which is incubating at Exo. His goal with Exo was ultimately one day to replace that with this. And so we went off on a kind of thought experiment, and we worked with this woman, Amanda Boxtel, a test pilot. And I asked her what she would want in an exoskeleton. And she said, well, I want this. And I said, what do you mean you want this? She said she doesn't want an exoskeleton at all. She doesn't want a clunky robot. She wants fabric. She wants a pair of cool pants. And I said, well, how about this? She said, yeah, that'll do. Why don't I make that for her? And I said, well, great, but I have no idea how. So we looked at it a little bit and we realized, okay, we've done 3D printed meshes. That's kind of all the rage. And we did that one with will.i.am years back. And there's certainly swarming robots, and we know they exist. We just didn't have that kind of brain trust in under our roof. And so we came up with some concepts for what a swarmed robotic mesh 3D printed custom based on individuals' morphology might look like. And we printed a bunch of these out for fun, but knowing full well that we didn't have the skill set in our team to get beyond this as a thought experiment. So short of that, we ended up scanning Amanda here at Exo. We scanned her sitting and standing, and we made a loft strand crutch. I made it for myself because I'll probably need it more than she does. And so we started designing the objects, and this is the industrial designer in us coming up with something that would make the robot not feel clunky, but would feel sensual and sculptural and beautiful. And there was an interesting tweak in this, that Russ thinks of his the exo robots not as exoskeletons, but exomusculatures, because the human skeleton still does all the load bearing it ever has. It's just the musculature is unaddressable after spinal cord injury. So they're really just recreating the musculature. So we wanted to really suggest that in the design of it, and with the sinews and the tendons and the fibers of the muscle. We 3D printed by now my company had been bought by 3D Systems, and I was the design director there. So we 3D printed sterling silver jewelry for the robot. And this is the final part. Now, why this is valuable for an exoskeletal robot is that these interstitial parts they confirm the robot against the body very accurately without being tight. That's important because wobbly robots, it's kind of like the steering on your mom's 72 station wagon. It just becomes wobbly and mushy. The more it is confirmed against the body, the better the overall results. And so this gives ultimately the best results. So we actually then took this out with us with Singularity, where I teach, and we took this out to Budapest, 2013 or whatever, assembled it in the hotel room overnight. Room service comes in while the robot is walking across the room, scared the shit out of her, which is just all kinds of satisfying. And then Amanda, these are the first steps she took in the printed robot, because we just didn't have time to test drive it in advance. And in front of the Romanian, Hungarian, whatever, government of Budapest, she got up on stage and walked across stage. Afterwards, we walked out and walked halfway across Budapest to Hero Square. It was a thought experiment, but it's a potentially interesting development in where exoskeletons might go. So the current project that Russ and I are doing and we're incubating at Exobionics is looking at getting people physical again and addressing some of the major health problems that the world is facing, because we are all too sedentary, playing too many games and not doing active things enough. Don't judge, we're all doing it. So the thing about it is, when I was a kid, I didn't do sports because I hated basketball, baseball, and football, which were the sports that my school offered. So I just figured I wasn't an athletic kid until I discovered windsurfing, snowboarding, mountain biking, and scuba diving. I realized, wait, actually, I'm plenty athletic. I just didn't like the crap they had to offer at school. So we're looking at, can we create an entirely new platform for entirely new sports that address an entirely new audience, and tell them that, yes, you can do really cool stuff. And you can, accidental byproduct, get really healthy doing it. So in this example that we have functioning at Exo, you get into the machine, you put on a headset, you grab the grips like any gym equipment, you have two active platforms suspending you, and you now physically interact with the virtual world haptically. And you have all full human range of motion, arms and legs. You have all types of haptics, from stopping motion to gravitational motion to anti-gravity motion to pushing and pulling, every other possible thing. And you can do it multiplayer, so you can physically interact with somebody else. These are right out of my venture pitch deck. But these are some of the activities. This activity, going out and blowing the snot out of other robots in the desert, in order to do it, you have to do reciprocating low rows, bench presses, and squats. Otherwise, you'll die fast. Flying your ornithopter here, you're doing chin-ups and step-ups and shoulder presses. To fly your motorcycle across the desert, step-ups and kind of a cross-country skiing motion. And paddleboarding is paddleboarding, but it's the core workout because you're on an unstable surface. So I'm just going to actually escape and show a quick video, unless you say don't because you don't have time.
No, we have to see it.
Okay, great, awesome, because it's just really cool. So the premise is that there are generations now who expect gamified everything, from brushing your teeth to training in anything to learning anything, and they won't accept the world unless it's gamified. We all know this. So here you are going into your virtual environment. This is what you see in VR. You become an avatar. The inverse kinematics recreates your body as whatever avatar you choose extremely accurately, because we have 6 points of 6 stuff trackers. You can choose your environment. So in this case, you're choosing a nice woodlands, and you can choose how you want to experience that environment. Now, sum total, you get a game out of it. So in this case, you're kind of scrolling through your different library of devices, and you choose your, not your flying machine, not your big killer robot, you choose your ornithopter. And so now you get to fly through your forest on your ornithopter. And there might be activities of all kinds: competitive, combative, collaborative, anything you want. And there's the exercise you're doing. You do this for 20 minutes, you're in really, really good shape. And when we want to increase the strength, we drop your glide ratio so that you have to work harder to stay aloft, stay buoyant. So it's a full arm and leg motion going. This is one we didn't show. It's a really cool version of Asteroids, the arcade game from when you're a kid. And here's a post-apocalyptic ripoff of Star Wars pod racer scene. You're in a really cool speeder. You're doing full body pitches to turn it and steer it. And here you're doing paddleboarding. You choose to go for a nice paddleboard in the Caribbean. So you choose your Caribbean setting, choose your paddleboard. And this also shows multiplayer. So, you know, in COVID and post-COVID times where you can't see your friends, you get to now all meet in virtual space and go for a nice paddleboard together while you're in a gym environment. So once the platform is built, the mechanical platform, all of the activity that you get to do in it of any kind of, for your own personality and your own kind of fitness goals, that all just kind of comes along for the ride. So we're hoping to get this into all gyms and family entertainment centers and any of those natural candidates.
Thank you so much, Scott. That was, firstly, your designs were stunning. And, you know, I seeing them all. And now I'm kind of wordless now with the directions that you're taking this. But I completely agree. That's the sort of experiences that we're opening up. And what you've done is you've really transitioned from prosthetics that are interfering with people's quality of life to things that are enhancing the quality of life, and then to saying, well, how can we all have enhanced quality of life? And that's a wonderful journey, and thank you. Michelle, it's a hard act coming after that, but I know you have such a human-centered experience of working with powered clothing or possibly exomusculature. Interested in what you call it and what your experience has been like. So Michelle, over to you.
Thank you so much, Andra. And thank you, Scott. That was really cool to see. And I love the human-centered design element of it. You know, I think that's probably going to be weaving in throughout this whole conversation. So as Andra mentioned, I was formerly with exSeismic, which we call powered clothing. And I'll just touch a little bit on my background to see how it all kind of plays in together. And of course, thank you for having me. It's really nice to be here and to see everyone's lovely face. Hope everyone is doing well. So I actually come from an academic background. I have a master's in biomolecular engineering. And for a number of years, I worked in a research lab on a nanotechnology tool for single cell research. And that was awesome. But after I finished my research and my graduate degree, I decided to switch into the aging and senior care space. So my entire career has been really focused on older adults in all aspects, products and services for older adults themselves, for families, caregivers, the senior living world, and anything that has to do with an older adult. And so my first job was actually at Aging 2.0, where we ran accelerators for startups in the aging space. that was really my first introduction to the whole world of aging, which there's thousands of startups working on products for older adults, which is really amazing. I was the first employee at Aging 2.0, so really built it out there, was there for a few years. And since then, I've worked at a number of companies as a consultant and full-time, including universities. I've worked for UC Berkeley, UC Santa Cruz, lots of different conferences, startups, and I'm also consulting for a senior living company itself. So kind of an array of different types of groups in the aging space, all focused on innovations. And of course, with older adults, and for me, universal design is really important. We want universal design to be supporting adults living happy and healthy lives. We want products that people at all ages would like and think are beautiful, and we don't want to design for just older people. We want to design something really lovely that we would all enjoy, and that could help us as we age in this world. And so my most relevant robotics experience was at Seismic, where we created powered clothing. Seismic creates a suit that has robotics built into it. It's not only functional, but it's very beautifully designed, makes the wearer feel joyous while wearing it, very fashion forward. The goal of the suit, of the powered clothing, is to support the core. So it provides a 25% assist on the core to help people have less fatigue and stay active longer. And the main customers for Seismic are active older adults and employee wellness, people who work in jobs where they stand all day for their job. We've had some pilots and customers in the employee wellness space along with the aging space. I'm not sure if people here have seen the Seismic suit, but I'm happy to play a video.
When I close my eyes, I see the trail, and I'm done wishing I was back out there, done thinking those days are behind me. I needed a shift, and that shift was Seismic. A fusion of apparel and robotics. A drive to get up and out there. The confidence to stand tall. And the energy to keep going. My feet are back on the trail, carrying me onward to what I love. Finding that perfect shot. That feeling, that's Seismic.
One of the interesting parts about that is it can be hard to see how much assistance the suit is doing because it is so subtle. And, you know, the person wearing it is not clearly in pain or impaired. And so to find, you know, I think it's a challenging concept to get across to people.
Yeah, that's very true. It is definitely something that someone at any age can wear. It feels very supportive. I definitely wore it a lot in my time at Seismic. It provides that strength and stability, and it's a smart system where it can also know how much support you really need. And it's intuitive. So as you're sitting, it will know as you move forward, as you put your shoulders over your knees, that you're about to stand up, and provide the exact muscle assist in those exact locations of where you need that assistance. So it's an amazing system. It was built over 4 years at SRI with a team of 50 designers and engineers before any commercialization ever happened. So it's a really beautifully designed product. And yeah, you know, as we age, that universal design is really important for a product for older adults to really want to buy, want to wear, and not have any stigma while they're wearing it. We don't need loud noises and things that might make someone feel uncomfortable, as this is a product that should be really seamless in someone's everyday life. They should just put it on like it's normal clothing and go about their day, and it should be helping support them living a happy, active, aging life. And And so, with that, in the aging space, it's all about really kind of maintaining independence and supporting engagement in people as we grow older. I've seen a lot of important innovations when it comes to activities of daily living. And with AI and predictive analytics, we can really support people in whichever setting that they're in. And assistive robotics and aging can not only mean supporting your body, but it can also mean a robotic kitchen for cooking, or a self-driving car, or actually a self-driving car connecting with your powered clothing. Can the powered clothing know your temperature, and can the car adjust the temperature in the car? Can it know where you're going automatically? How do these technologies play within each other to really have that seamless, long connected experience? So that's kind of where I'm coming from. And yeah, that's what I was prepared for this. And so thank you.
Thank you so much, Michelle. And I'm always fascinated by how this research was originally, as so much in medical robotics, was originally part of DARPA or Defense Force initiatives.
That's
and yet it can be repurposed for everybody in quite different fashions. And one of the things that we don't talk about as much as we should is the huge impact of the aging population and how we're going to deal with that, where robotics is really one of the only answers, given the way the demographics are shifting so rapidly. And I know China and Japan have are at the forefront of being aware of this. And I think there's a lot of interest from Japan in the seismic powered.
There is. Yeah, thank you. So a lot of our investors at Seismic were from Japan, and a lot of our partners. And we actually opened a studio. I was part of the team that opened a studio in Japan. So we were able to open like a retail store where people could come in and see a live demo of the product, sign up for a waiting list, and kind of market our product over there in person. And we had a lot of success with that. There was a lot of interest. And again, they have not only an older demographic of population and citizens, but an older demographic in the workforce. And so we were working with, for example, a construction company where their median workforce was in their 40s and 50s, compared to the US, where the median workforce for construction is a bit younger. So we definitely, this type of power clothing and this type of robotics can really support older adults staying engaged in their vocational lives, occupationally. That really is, staying productive is really important to aging, not being isolated, and really feeling like you have that meaning and productivity to be focused every day and have that happiness. That's very important for mental health. So yeah, there's a whole kind of range of things that it's great for. But yeah, Japan has been an awesome partner, and they have the tools there to really get something like Seismic off the ground, and they've been amazing partners.
That's great. And I see some questions around some of the mechanical aspects, but I know Yves has been specializing in the mechanical engineering aspects of exoskeletons. So I'd love to hear from you now, Yves. Thank you so much, Michelle.
Thank you, Andra. And I just want to say it's really, really great to be here, especially with seeing some of the really, really interesting work that people are doing out here. And I think actually Michelle set me up really well for a good portion of my talk. So I'm going to share my screen. This is about prosthetics and exoskeletons and wearable clothing. And so I think from a control standpoint and actually making sure that these devices do what we want them to do, I think that they're seen sometimes as notably different areas, but I think as made evident by having this kind of seminar here, that there's actually a lot of similarities in between these things. And so for prosthetics, we might see that this is kind of a device that's in series with a human, whereas an exoskeleton is kind of working in parallel with somebody. The areas and the the users of these devices might be targeted a bit differently, where, you know, we have amputees for prosthetics, where I say able-bodied in quotes because I think exoskeletons go much further than just doing something that's like Iron Man or Secret Soldier type stuff. I think there's actually a lot of great uses in terms of what we can do for rehabilitation as well. But I think, you know, when you look at the morphology of people who are using this, right, more often than not, with exoskeletons, you're talking about people with 2 legs and using this for some end goal, whereas prosthetics have single legs. And then I think, you know, we just have different kind of considerations. I think, you know, Michelle was talking about that it's about 25% assistance with the seismic system. And so, you know, that is maybe different than a prosthesis, which needs to recreate the positions and the torques that you see in a human leg. But one thing I think that really brings all of these things together is how we control these devices. And so, you know, I think there are kind of 2 main types of control. You could really get into a lot of things about control, but at the basis, I think there's 2 ways that we can kind of group the way we control prosthetics and exoskeletons. You have high level control, which is kind of recognizing what is it that the user of this device wants to do. So I think a lot of times we'll hear buzzwords of big data or machine learning or AI. And generally when you're hearing these words, that has to do with this high level control. So an example for this, you know, I love to cook food. And so, you know, having like a recipe, essentially, you can think about your recipe or gathering all the ingredients and utensils that you need to cook. That's kind of like high level control, right? You can say, I want to make chicken cacciatore. And so to do that, you know, I'm going to need chicken, I'm going to need this pasta, you know, need my spices. And so that's kind of this overarching theme of, all right, what is it that I want to do? Whereas with low level control, right, that's actually executing this, right? And so there are a few different types of low level control. You can control a position, you can control a torque, or you can do something that's called impedance that I'll talk about in a little bit. But I think what's really important about low level control is that you need to make sure you do this well so that you're actually executing the activities in the way that you think. You know, if we're kind of talking about a cooking analogy and you think, okay, do I need a half tablespoon of salt or a half teaspoon of salt? That will make a big difference in actually, you know, the end flavor that you're going to have. And so with low level control, you're actually making sure that, you know, you measure this ingredient correctly, and you're making sure that your output is what you think it's going to be. And so in my lab at the University of Michigan, we actually use an exoskeleton to help us measure properties about the human body. And so I think one thing that is interesting about our approach about using this exoskeleton is that often I think exoskeletons, even like the wearable clothing and things like seismic, right, are seen as assistive devices. And that is definitely a large area where I think we can use exoskeletons to help increase the quality of life of the users. But I think, especially as we make technological advances, we can also use these exoskeletons to sense information. So similar to what Michelle was saying, right? You maybe can have wearable clothing that is sensing your temperature or sensing something about you. And then from the information it's sensing, right, you can then make decisions. And so with this exoskeleton we have, this is just a small diagram about kind of some of the inner workings of this exoskeleton. And 2 things I really want to point out is that we have this rotary encoder, which measures positions with sub-micron accuracy. So even smaller than the accuracy of a human hair, which gives us really great position information. So the output of somebody's leg, for instance, who's in this, we can measure it really finely. And the other thing that I want to point out is that we have a fiberglass spring in here. So it is with this fiberglass spring in our exoskeleton, it creates something called a series elastic element. And while the actual name of that isn't important, what is important is that having this elastic element or having this spring in our exoskeleton allows us to measure torques because we know how stiff this spring is. And then using some of these encoders that we have, this linear encoder and rotary encoder, we can measure how much that spring deflects. And from that information, right, we can now know the torques being applied to this exoskeleton and use it as a sensing device, as well as, if we so chose, right, using it as an assistive device. So one of the things that we actually like to measure in our lab, right, is this thing called joint mechanical impedance. And so one, what is impedance, right? In its kind of highest form, it is the relationship between an input position and output force, which is great. But I think maybe a more humanizing way to think about it is think of a spring or think of a rubber band, right? If you have a really stiff rubber band and you stretch it just a tiny amount, right? The rubber band wants to go back to its initial position. And so you're going to have a small torque that's kind of created, or a small force that's going to be applied to you to make it go back to its original position. Whereas if you have this very stiff rubber band, right, and you stretch it really far, you're going to have a really strong force kind of bringing you back to your initial position. And so this kind of idea of saying that we have stiffnesses, or we have springs in our body, or we have other things that kind of regulate how we can go between position and force, is something that our body does and is actually useful in terms of how we relate to being disturbed. So for instance, if you're clumsy like me, you've definitely had plenty of times where you're walking and maybe you trip on something, trip on a rock, or trip on a line, or trip on air if you're in my case, right? And so with that, we have our body, it's thought that our body uses this kind of impedance idea by modulating our stiffnesses and modulating other properties that allows us to respond to when something's happening that we weren't expecting. And so we think, this can be really actually beneficial when we're talking about controlling wearable devices. For instance, in a prosthetic, if we have a prosthetic leg, then we can recreate kind of these stiffnesses. And in this case, I'm also referring to damping. So let me take a step back and say, this is an equation right here that could be used to describe impedance. And what this is really just saying, even though there's a bunch of terms, is saying that the torque that we get is equal to some stiffness, for instance, like our rubber band that has been stretched, except in this case, right, we're talking about your joints as some kind of stiffness, some kind of spring, plus there's a contribution of a damper, so something that kind of releases energy based off of how fast you're moving. And so, by recreating, hopefully, this behavior that we see in the human body, we're hoping that, with, let's say, a prosthesis user, we can decrease the energy that they are expending when they're trying to do a task, such as walking, such as running, maybe even jumping. And so I think, that becomes really important because it's been mentioned before that really we care about the quality of life. I think that while there are incredible technical innovations that we end up coming up with throughout the world, I think really the base question that we should be asking ourselves is, how is this helping people, right? How is this changing the lives that people are living, especially if they've had some kind of potentially traumatic injury that has robbed them of a limb, or maybe robbed them of use of their limb, such as a stroke, for instance. And so being able to have people, because generally, like prosthesis users, for instance, use far more energy just to walk than people who are walking, who are able-bodied potentially, like myself. They use so much more energy. And so that all that energy that they're using just to get from point A to point B, right, could be used to actually do something they enjoy, such as dancing, such as going to talk to their families. And so I think it's important that we can hopefully make these robotic wearable devices that we are attaching to humans in some way, shape, or form, make these as close to their original bodies as possible so that they can go and get back to their original life, right? And so, there are some graphs right here, which is just some work that we've previously done in my lab, kind of taking these properties that I've been talking about from this equation, right? The stiffness and the damping, and just characterizing how do these properties change as people walk. So the top two, the light blue graph, is showing how the stiffness and damping properties change as you go through kind of one gait cycle, or more or less from having heel contact on one side, so putting your heel down, to heel contact again on that same leg. That's called one gait cycle, but you can think of it as a stride, 2 steps. There are a few ways to think about this. And so basically, just looking at, now that we have the ability to measure these properties, both at the ankle, and these are some preliminary results below in the dark blue for the knee, we can hope to recreate these devices, or recreate rather this behavior. And so from that, I think that gives us some interesting areas to explore in the future. So like I mentioned before, right, we can see what are the effects on users, right, if we have these prosthetic devices and hopefully we are creating human-like behavior. What does that do for somebody using a prosthetic? But for instance, right, it's not just a prosthetic. I think we can also apply a similar mindset to people using an exoskeleton, right? Let's say you are a survivor of stroke, or maybe you have cerebral palsy or something of that nature, right? How, if we know, let's say, what the able-bodied or the average, and I use that term in quotes because what is really average, but you know, if you can have the able-bodied impedance curve, for instance, as it changes over an activity, right? And then we can measure, well, what is the actual impedance of somebody who has survived a stroke, right? We can look at these differences and see, okay, is there a way that we can apply a robotic intervention so that we can hopefully recreate the overall behavior that we would expect to see in able-bodied folks who maybe haven't had a stroke or do not suffer from cerebral palsy or things like that. So I think that's a great area, you know, to explore in the future. I also, so, you know, right now we're talking about low-level approaches, and in my lab, because I'm really trying to use this exoskeleton as a measurement device, right? I use a lot of low-level approaches just to make sure that the exoskeleton is indeed measuring positions and measuring torques correctly, and being transparent, hopefully not setting off or not throwing off data measurements. But I think, you know, combining a low-level approach, for instance, of recreating this impedance trajectory, and then also having these high-level approaches of having, you know, some kind of AI unit or some kind of machine learning technique to decide, oh, I see there are stairs coming up, so I want to prepare my body to go upstairs, or I see that I want to jump, I see that I want to run. How can we make these transitions seamless? Because, you know, that's something generally that we as human beings do. And I think being able to create that in the robotics that we use, in the robotic platforms that we use, I think could be really interesting and could have a lot of utility. And then lastly, so we also, right, have measured now how this impedance term, or how this impedance trajectory changes, in our case over walking, but we have the ability to measure, right, over tasks. And so I think this also can be very useful in looking at rehabilitation. So if I tear my ACL, for instance, or I tear some ligament in my knee, I can go and know what the average curve looks like, for instance, for somebody's stiffness or somebody's impedance properties. And then I can measure, all right, immediately post-surgery, what do my impedance properties look like, right? And then after a month of rehabilitation, maybe I can see, okay, am I trending in the right direction, right? How are my impedance properties changing? And hopefully we can use this as a way to benchmark kind of the rehabilitation process, and give clinicians and doctors, and really most importantly, the end user, the patients, give them just some more information so they can make some more informed decisions. So with that, I just want to say thank you very much. And also, while I have the time, I was going to say it's my mother's birthday, so I had to make sure I shout her out on this platform and tell her happy birthday.
She must be so proud of you. That was an amazing talk. And I see it's got all the roboticists in the audience excited. The chat's full of questions for you. And thank you very much for elaborating there. Oh, Hamayal, another hard act to follow coming after Yves, but in a sense, you're a culmination of a lot of these ideas, and you're putting it into practice. And so I'm really interested in hearing what you're doing with smartARM. And yeah, thank you. Over to you, Hamayal.
Sounds good. Andra, thanks for hosting this platform. It's been, like you said, amazing to hear what everyone's been up to. And I think Yves actually set me up really well in terms of the problem that we're working on. And I think it can kind of best be described as we're focusing or honing in on the low-level application of AI in prosthetics specifically. So thanks for that, Yves. And so sort of give you context about how all of this came to be. You know, a couple of years ago, when I was looking around myself and seeing what really excited me, I saw that and AI is more rampant around the world than it has ever been before. And with it, for the first time, the ambition to do amazing things with it was being increasingly democratized by a lot of tools, or by a lot of easy to use tools. Think about it, living in 2021, we are in an age where everything around us, every part of our society, in every country, across every industry, is being changed because of technology. And so the impact that we all can have is enormous, and with it, the opportunities are enormous. But I also believe that there is a profound need for responsibility that we all have to collectively exercise, given the opportunity that we've been given. The impact we're all going to have is based on the choices that you and I can make. The problems and challenges we choose to get behind. So with that said, I'm particularly fascinated by what these advancements means for creating devices, like everyone else here mentioned before me, to empower people with different abilities. And it's exactly why I started my bionics company, to make affordable robotic hands that can see. Now, to kind of lead you through that a little bit, I'll share my screen. Yeah, so essentially the problem we're tackling here is, current incumbent bionics we saw were very expensive, but still came with somewhat limited functionality. Currently, a lot of the hand amputees that we've been speaking to, or we spoke to, they felt very neglected with and frustrated with bad user experience, to the point where about 90 to 95% of the global hand amputee population didn't really have access to prosthetics because of the high cost. Do pay a lot of money and still claim to feel limited in terms of the functionality that they got. And so the way we kind of went about solving this and developing something better, trying to get the slides to move here, was using 3D printing and machine learning to provide a bionic hand that's affordable yet still very powerful. And the way we do that is we took a camera and embedded that right into the palm to identify any object that the user wants to pick up or interact with. And our machine learning algorithm running on the computer on board calculates the best grasp for that object based on its shape, geometry, size, what have you. So to kind of walk you through that, let's say you have a bottle in front of you that you want to pick up. As soon as the hand sees it, it begins cross-referencing it with a bunch of different objects it has in its database. And once it finds an ideal match, it knows the pre-recorded position or grip pattern for that object, allows you to pick it up successfully. Now, it's been quite the exciting journey, and to kind of give you a sense of where we started from, this was about 2 years ago. We came up with this at a hackathon, and that's what our product looked like. It was a quick 3D printed hand, kind of taped together, standard hobby servo motors, and we had connected it to a Raspberry Pi at the time. We took that, and that's essentially, Andra was mentioning earlier, we won this huge Microsoft competition with that, which was quite the journey. So once we'd won that, we saw that there was a lot of interest around something like this. And so we developed a better version. Sorry, this was the version we developed as part of that competition. It looks a bit more polished, but still not exactly something you'd put on anybody. From there, we took that and started working on seeing how we could turn that into a device that was actually wearable. So this was the early version of that. Currently, we're taking everything we've learned. We've verified the technology and kind of the way it interfaces with users on the human level. And we're working on our final production unit, which you can see in front of you. It was inspired by user input and whatnot. And actually, I have a clip here of one of our early testers using it and giving us feedback. So everything you're about to see here, she's not controlling what the hand is doing at the extremity. That's all being taken care of by the robot. The only thing she's really controlling is the trigger, which is located in her socket over here. So that just tells the hand when to open and close, but the what and the how, that's all taken care of by the hand itself. So I'll play it over here. And so one of the really neat things about this is what it allowed us, or what it allowed her to do, is conventionally, there's always a certain amount of learning. A lot of users describe it to us like the way they're done conventionally. They describe it to us like trying to drive a car with chopsticks. It's not necessarily always intuitive. But in this case, this was just a couple of seconds after she put it on, never having used a device, a prosthetic device in general before. Within a couple seconds of that, she was able to get it going and actuating and interacting with stuff, all just found in her kitchen. So yeah, there's that. But yeah, it's been quite the exciting journey. You know, started at a hackathon. From there, we caught the attention of Microsoft, and they do this huge competition with about 40,000 students from around the world. At the time, I was still so we entered that, and kind of overnight, once we won, we found everything to blow up, and which took us on a journey around the world. Turned out a lot of people, especially future users of the product, were interested in something like this. And that kind of culminated with a TED Talk that I also did right before the pandemic ended. But it's been an exciting journey, and we're actually looking to launch our product this summer. So gearing up and getting a lot of users on board and starting to take pre-orders. And one of the really neat things that we're doing is we're trying to work with users from start to finish. And by doing that, we're trying to become geographically agnostic as well. So, you know, right now, if you want a prosthetic device, it involves you going into a clinic and getting manually, in a lot of different places, manually having to get a mold made of your residual, which you know, technicians or prosthetists then take to make your socket. But what we're trying to do is trying to leverage existing 3D scanning technology that you find on a lot of phones these days. If you have an iPhone, it's the Face ID thing that unlocks your phone. Turns out you can get a really high quality scan of a residual limb using that alone. And so what it allows us to do is work with users just about anywhere in the world. We can get them to digitally send us, and we coach them through this, but digitally send us a scan of their arm. And then we work with that scan with prosthetists on our team to build out a socket and ship it to them no matter where they are in the world. So very excited about that. And that's it for me. Hard to top what kind of everyone else has mentioned so far, but happy to take questions once we get to that portion of tonight.
Well, thank you so much, Hamayal. I think everybody managed to exceed a very, very, very high bar. And there's a lot of excited questions in the chat. We usually do finish around now. So what I will hope is that we can still address some of the questions in the chat. And I'm very pleased that you're in the process of launching. I think we've been talking a little bit about this, and I had no idea that I was going to see so many amazing advances in these areas tonight. But not only advances, a deeper understanding of the rationale behind some of these developments and the mechanics, the how of it as well. I know I'd read that many of the veterans would, rather than use the prosthetics that were available, would prefer to use, I was told, a ruler with an elastic band on their hand, because it was able to do the same amount of tasks and was more comfortable. And that to me says that it's a very difficult problem, and there's a lot of improvement available that we need to be taking. And it sounds as though you're working on this improvement. And look, I want to really thank you all for speaking tonight. Ken, did you want to give us some closing words?
Thank you for putting together such a fantastic session. Absolutely inspiring and riveting to see these ideas and thinking about this idea that we can actually extend human capabilities in this way, that the prosthetics are so helpful for bringing people out of limitations, but also extending them way beyond what their current potential is. So I'm really excited about this and all this work, and I would love to have another session on this very topic in the future.
think we will need to talk about human augmentation next, or perhaps some of the questions that are coming up around maybe some of the details. We were looking at the sensor feedback and the roles in rehabilitation. And so the areas of haptics and sensor feedback, I know this is going to be part of the Avatar X Prize challenge, which is coming up. But Scott really did open the discussion today with the notion that we're moving past simply making something bad a tiny bit better. And we're improving the quality of life, and improving the quality of life is applicable to everyone. And Michelle really brought home to us the beauty of developing products that can help the aging population be active agers. And as I'm certainly now one of those aging population people, I appreciate that. But I also love the idea of being able to do virtual exercise in my potential ethereal gym. But then Yves really explained some great concepts and the way in which the biomimicry loop is closing a little bit again on how we're learning from nature and applying it to assist people. And Hamayal's journey is just amazing. It's incredible what he's accomplished in such a short time. And we'll be seeing some really good things in the next few months there. And I love the vision. So I think we'll call it a wrap for the evening. Thank you all for joining us. And we'll have to come in with the next topic on inclusive robotics, following the trend towards augmentation or feedback. Perhaps feedback is the direction. We'll think a lot about what's been talked about tonight, and look forward to seeing you in another month's time. Thank you, everybody.